In the remote wilderness of eastern Russia, gold prospectors have unknowingly discovered something far more valuable than precious metals. Hidden within fragments of ancient meteorites lie microscopic structures that defy the laws of classical crystallography, natural quasicrystals of extraterrestrial origin. These mathematical anomalies, once thought impossible by the scientific community, are now revolutionizing our understanding of structural order in the universe. Join us on a journey from the frigid streams of the Koryak Mountains to the frontiers of materials science as we explore how these cosmic impossibilities are changing our fundamental understanding of nature itself. For centuries, crystallographers operated under a strict set of rules. Crystals could only display certain symmetries, twofold, threefold, fourfold, or sixfold rotational patterns. This wasn't just scientific convention, it was mathematical law. The hexagonal structures of snowflakes and honeycombs exemplified these acceptable patterns. But in 1982, Israeli scientist Dan Shechtman observed something that shouldn't exist, a material with five-fold symmetry. This observation directly contradicted established crystallographic principles. When Shechtman presented his findings, the scientific community responded with ridicule. Nobel Prize winner Linus Pauling famously dismissed his work, declaring, "There are no quasicrystals, just quasi-scientists." Shechtman had committed the scientific sin of challenging paradigm. Yet his evidence was irrefutable. These structures followed precise mathematical rules but never exactly repeated themselves, creating a form of ordered chaos that defied conventional categorization. Shechtman's persistence eventually led to a complete paradigm shift in crystallography, vindicating his work and earning him the 2011 Nobel Prize in Chemistry. The mathematics behind quasicrystals connects to work done by Roger Penrose in the 1970s, well before their physical discovery. Penrose demonstrated that just two shapes could tile an infinite plane without ever creating a repeating pattern, a mathematical curiosity that seemed purely theoretical at the time. These Penrose tilings turned out to be the two-dimensional analog of what quasicrystals do in three-dimensional space. What makes quasicrystals truly mind-bending is that they require higher dimensional mathematics to explain their three-dimensional patterns. Scientists must use 5- or 6-dimensional mathematical models to describe how these structures organize themselves in our three-dimensional reality. It's as if these materials exist partially in higher dimensions, with our world seeing only a three-dimensional slice of their complete pattern. This connection between physical materials and abstract higher-dimensional mathematics represents one of the most profound intersections of theoretical mathematics and observable reality in modern science. For decades after Shechtman's laboratory discovery, quasicrystals remained artificial curiosities, created only under carefully controlled conditions. The idea that nature could spontaneously produce such mathematically complex structures seemed implausible. This changed in 2009 when mineralogist Luca Bindi from the University of Florence examined museum samples of an unusual meteorite and identified what appeared to be natural quasicrystalline structures. The claim was so extraordinary that Princeton physicist Paul Steinhardt, who had theoretically predicted quasicrystals years earlier, initially suspected contamination or misidentification. To verify this remarkable finding, Steinhardt and Bindi needed more samples traced to their original source. This quest led them to the remote Koryak Mountains in far eastern Russia. In 2011 and again in 2016, they organized expeditions to this isolated region, navigating challenging terrain and bureaucratic obstacles. Their persistence paid off when they recovered additional fragments of what became known as the Khatyrka meteorite. These cosmic fragments contained aluminum-copper-iron quasicrystals with perfect icosahedral symmetry, displaying the impossible five-fold symmetry from multiple viewing angles. Most remarkably, isotopic analysis confirmed these structures formed naturally in space approximately 4.5 billion years ago during the early formation of our solar system. The presence of these quasicrystals poses additional mysteries beyond their forbidden symmetry. The Khatyrka meteorite contains metallic aluminum, which typically oxidizes rapidly in the presence of oxygen. This suggests the quasicrystals formed in the oxygen-poor environment of outer space, preserving their structure as they journeyed to Earth. But how exactly did they form? Research published in 2021 by Steinhardt and colleagues in the Proceedings of the National Academy of Sciences revealed that these natural quasicrystals likely formed through hypervelocity impacts between astronomical bodies. Using advanced mineralogical analysis and shock physics modeling, they demonstrated that only the unique high-pressure, high-temperature conditions created during meteorite collisions could provide the precise environment needed for these structures to form. These cosmic collisions generated pressures above 20 gigapascals and temperatures exceeding 2,500 degrees Celsius, conditions virtually impossible to find naturally on Earth. The meteorite contains a complex history recorded in its mineral assemblage. Metallic copper and aluminum, which don't typically coexist in natural settings, were forced together under these extreme conditions. Microscopic examination reveals shock veins and melt pockets where materials briefly liquefied before rapidly cooling and crystallizing into unusual configurations. Computer simulations suggest that the impact event occurred at velocities exceeding 5 kilometers per second, a cosmic collision of extraordinary violence. The discovery of natural quasicrystals and meteorites has prompted researchers to reconsider other extreme environments where these structures might form. Current candidates include the deep interiors of gas giant planets like Jupiter and Saturn, where immense pressures and temperatures create unique material conditions. The near-surface regions of neutron stars, with their incredible gravitational fields, might also generate quasicrystalline structures in their crusts. Even more exotic possibilities include the shockwaves of supernova explosions, where rapid cooling from extreme temperatures could potentially create these ordered yet chaotic structures. Some theoretical models suggest that quasicrystals might even form in the accretion disk around black holes, where extreme gravitational forces create material conditions unlike anywhere else in the universe. Each environment offers unique combinations of temperature, pressure, and cooling rates that might produce different quasicrystalline structures. As our ability to model these extreme conditions improves, scientists are developing new predictions about where in the cosmos we might find more examples of these mathematical anomalies. The existence of natural quasicrystals challenges our fundamental assumptions about order in the universe. As Paul Steinhardt noted in a 2019 interview with the Journal of Cosmology and Astroparticle Physics, these structures occupy a fascinating middle ground between ordered crystals and disordered materials. They follow mathematical rules, but never exactly repeat themselves. This property places them in a unique category that bridges order and chaos, determinism and randomness. Perhaps most fascinating is the connection between these cutting-edge discoveries and ancient art. The mathematical patterns found in quasicrystals bear striking resemblance to medieval Islamic mosaics, particularly those found in the Alhambra Palace in Spain. These architectural masterpieces use geometric patterns with 5-fold and 10-fold symmetry centuries before modern mathematics could explain such structures. Somehow, these artisans intuitively discovered patterns that would later be explained through Penrose tilings and aperiodic mathematics. This connection between ancient art and modern materials science suggests a deeper intuitive understanding of mathematical principles that transcends cultural and temporal boundaries. It raises profound questions about how mathematical truths may be discovered through different paths, whether through artistic intuition or scientific inquiry. Beyond their theoretical importance, these cosmic quasicrystals exhibit properties that could revolutionize materials science. Research led by Tsunetomo Yamada at Hiroshima University in 2022 demonstrated that specific quasicrystalline structures exhibit nearly perfect thermal insulation properties while maintaining electrical conductivity, a combination previously thought mutually exclusive. In conventional materials, good electrical conductors are also good thermal conductors, as both properties rely on the movement of electrons. Quasicrystals break this rule through their unique structural arrangement. This counterintuitive combination could lead to breakthroughs in thermoelectric materials that convert heat directly into electricity with unprecedented efficiency. Additionally, these materials display extremely low friction surfaces. The non-repeating nature of their atomic arrangement means there are fewer points where surfaces can catch on each other, resulting in some of the slipperiest solid materials known to science. NASA researchers at the Glenn Research Center are actively investigating quasicrystal-inspired coatings that could significantly reduce wear on spacecraft components during long-duration missions. Some quasicrystalline materials also demonstrate unusual optical properties, including selective transmission of electromagnetic waves. This could lead to novel photonic devices and more efficient solar cells capable of capturing specific wavelengths of light with minimal energy loss. The discovery of natural quasicrystals and meteorites has profoundly impacted multiple scientific disciplines. In crystallography, it forced a complete rewriting of textbooks and the very definition of what constitutes a crystal. The International Union of Crystallography had to formally change its definition of crystals in 1992 to accommodate these structures. In astrophysics, quasicrystals serve as cosmic messengers, carrying information about extreme conditions in the early solar system that cannot be replicated in laboratories. Their study provides unique insights into the collision events that shaped our planetary neighborhood 4.5 billion years ago. For material scientists, they represent an entirely new class of matter with properties that defy conventional understanding. And for mathematicians, they provide physical manifestations of abstract concepts in higher dimensional geometry and aperiodic order. This cross-disciplinary impact continues to grow as expeditions search for new varieties of natural quasicrystals in meteorite-rich regions like Antarctica and Chile's Atacama Desert. Each new discovery expands our understanding of what's possible in natural systems and challenges us to reconsider our assumptions about order and structure in the universe. The story of quasicrystals reminds us that nature often operates beyond the boundaries of our theoretical frameworks. When Dan Shechtman first observed quasicrystalline patterns, he famously told himself, "There can be no such creature," yet the evidence before his eyes contradicted everything he had been taught. His willingness to question established wisdom, despite facing ridicule from scientific luminaries, eventually led to a Nobel Prize and a fundamental shift in our understanding of matter. This pattern of discovery, where observations that shouldn't be possible lead to scientific breakthroughs, has repeated throughout history. As Princeton's Paul Steinhardt reflected, sometimes the most profound discoveries come from finding things that, according to our best theories, shouldn't exist at all. The journey from Shechtman's controversial laboratory observation to the discovery of natural quasicrystals and Russian meteorites spans decades and crosses multiple scientific disciplines. It demonstrates how nature's complexity often exceeds our theoretical understanding, and how persistence in the face of established dogma can lead to revolutionary insights. In this intersection of mathematics, materials science, and cosmochemistry, we find a humbling reminder of how much remains to be discovered about our universe and its fundamental organizing principles. From the remote streams of eastern Russia to the frontiers of materials science, quasicrystals represent one of the most profound scientific journeys of our time. These structures, once dismissed as theoretical impossibilities, have forced us to rewrite the rules of crystallography and reconsider our fundamental understanding of order in the universe. The Khatyrka meteorite, with its extraterrestrial quasicrystals formed in cosmic collisions billions of years ago, connects us to the violent birth of our solar system while simultaneously pointing toward future technologies that could transform energy production, space exploration, and materials engineering. Perhaps most remarkably, these cutting-edge discoveries echo patterns found in medieval Islamic art, suggesting that mathematical truths can be discovered through multiple paths across different cultures and eras. As expeditions continue searching for new varieties of these cosmic anomalies, each discovery expands the boundaries of what we thought possible. The story of quasicrystals serves as a powerful reminder that scientific progress often begins when we confront observations that challenge our most fundamental assumptions, when we find things that, according to our best theories, shouldn't exist at all. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.